Okay, in last class we discussed about the microwave spectroscopy, and we have to discuss the instrumentation part of that microwave spectroscopy that we will discuss about along with the instrumentation of IR spectroscopy. So now we will start a new topic, which is the infrared spectroscopy. Infrared spectroscopy or IR spectroscopy. So first we will discuss some of the key points about this IR spectroscopy. So first point is that it can be found at this IR spectroscopy, which is which is one way is that we can say this IR spectroscopy. In IR spectroscopy, we use infrared, near infrared spectra. Otherwise, you can say that the molecule vibrational spectroscopy. Okay, in that case, this is also called as vibrational spectroscopy. Vibrational spectroscopy. So in the case of vibrational spectroscopy or IR spectroscopy, and this can be found in near infrared region, can be, I'm just writing it as in short way, so it can be found in near infrared, that is 1 micro to 100 micro range region. So this is the region where we use this IR spectroscopy. So vibrational spectroscopy or vibration of molecules which can be found in near infrared region. Okay, so we are using in that electromagnetic spectra, we are using this near infrared waves to study this vibrational spectroscopy or vibrational spectra of different molecules. So that is first point, which is operating or which can be the spectroscope technique uses the near infrared radiation. Second one is that in order to have this vibration of molecule, we need a changing dipole moment. Okay? So in order to have this, to have vibrations or vibrational spectra, in order to get the vibrational spectra, the molecule, first of all, the molecule should have changing or we can say oscillating dipole. Changing dipole moment with vibration. When the vibration happens, there should be a change in its dipole moment. Only such molecule will be show this vibrational spectrum. Okay, so in order to show this vibrational spectra, the molecule should have a changing dipole moment with vibration. So we can say homonuclear diatomic molecules homonuclear diatomic molecules will not show higher spectra. Why? Because when you are considering homonuclear diatomic molecule, for example, oxygen, O2 molecule, so we have two oxygen are bonded each other. So in this case, we do not have any permanent dipole moment, first of all. And even if they vibrate, we cannot get any dipole moment because these two are having same charges separated by a distance. So the dipole moment is zero. In order to have the dipole moment, we need opposite charges which are separated by a distance. But in this case, we have single molecule, so we'll be having same charges for those molecules, for those atoms, oxygen atoms. We'll be having same charges, so they will not form any dipole moment in this case. For example, we are considering O2, okay, or any such kind of molecule which are homonuclear, okay, which are homonuclear diatomic molecule. They will not show any IR spectra because they do not have permanent dipole moment. So even they vibrate, they will not produce any change in dipole moment. Okay. So this kind of molecules with homonuclear or same atoms, they will not show any any infrared spectrum because they are not having this permanent dipole moment, and then they do not have any change in dipole moment. So normally having in this kind of this kind of vibrations, normally having a very high intense peak along with less intense diminishing or faint lines. If you're analyzing that spectra, so in that case we have normally we'll be having those spectra will be having very intense peak along with less intense less intense peaks. So we'll be having very high intense peak as well as very low intense peak along with the peaks which are called as fundamental bands and the low intense peak which are called as overtones that we will discuss in the upcoming sections. Okay, so what is the basic principle behind this uh, vibrational spectroscopy or IR spectroscopy? For that, I will just show you how the molecule vibrates when they are uh, absorbing some particular radiation. Okay, suppose if you are having a molecule, let's say this is your sample, which consists of some particular molecule, and if you give some radiation to the sample, and when they absorb this radiation, they will produce some kind of oscillation. So in the last class we discussed, or last section we discussed about the microwave spectroscopy. So when we give some microwave spectra to the sample, to the molecules, they start rotating. Okay, they will absorb that particular radiation and they will start rotating. If that rotation frequency which matches with the radiation which is coming, then it will absorb that particular radiation and it will start rotating into some higher energy levels. So that we explained. That is in the case of rotational spectroscopy or microwave spectroscopy. So in order to have that rotation, we need microwaves. More rotational spectroscopy, we need microwaves. So if a molecule which is rotating and which is coming to down to its energy level from a higher excited energy level, then it will emit radiation which is in the microwave range that we discussed in the last session. But in this case, we are considering the vibration of molecules instead of rotation. And for vibration of molecules, the incident wave should have a frequency which is equal to that IR frequency, infrared radiations frequency, which is in this near infrared region. So we need the radiation should have a frequency or wavelength which is in this range. Then only we will get that vibration of molecules. Okay? So the vibration of molecules can happen when you are providing infrared region to that particular molecule. And if that molecule have some kind of vibration which is equal to this incoming radiation frequency, vibrational frequency equal to that incoming radiation frequency, then that particular frequency will get absorbed by this molecule. Okay, then we can detect which frequency is absorbed by this molecule and we can say what kind of molecule it is. This is IR spectroscopy. Okay, otherwise if this particular molecule is vibrating and when it is coming to its ground state from that excited state level, suppose vibration which is happening in an excited energy level or higher energy level, when it comes to some lower energy level, it will emit some radiation region. It will emit same radiation which is in the infrared. So in both way we can study the molecule. One way is that absorption of this infrared radiation by providing some infrared range of frequencies. Otherwise, you can examine any molecule's vibration and it will emit the infrared radiation and study that emission spectra of that particular case and study which radiation is coming up. So both way you can analyze. So what kind of vibration can be possible in this kind of molecules that will discuss. So from this, we can see there are basically in this case 6 vibrations which is shown here. Okay. In the first case, we have this symmetric stretching. This one is symmetric stretching, and second one is anti-symmetric stretching. Then we have this rocking, then we wagging, twisting, and scissor. Okay, these are different kinds of vibrations. Among these, we have two. We have two different modes of stretching vibrations. One is symmetric stretching, and second one is anti-symmetric stretching. Symmetric stretching and anti-symmetric stretching. Then these are bending modes. Okay, these two first two, which are the stretching modes, and the remaining 4 are the bending modes. Okay, and I will show you how it is happening. So now, if you focus on this stretching mode, then we can see these 2 atoms are stretching from this central atom in equal amount. Okay, so this is called as symmetric stretching. First one. And in the second case, you can see the stretching of these 2 atoms, that is in green color, which is not in equal amount. One stretch, when one stretches, the other one compresses. Okay, so these 2 atoms which are stretching, when this happens, this symmetric stretching happens, both atoms stretches, then compress, then stretch, and then compress like that. Okay, so they will be doing this in the same time. Okay, both will be having. Suppose this atom is in the stretching mode, then it will be in stretch. Both will be in stretching mode. If this atom is in the compressed mode, then this also will be compressed. Both will be having same mode. Okay, then it is called as symmetric stretching. Both are having same kind of vibration. But in this case, when you are considering anti-symmetric vibrations, we have one particular atom which is stretching, okay, which is going away from this central atom. The second atom which is coming towards that central atom, or it is the compression which is happening. So in this case, these two modes are different. One is stretching, one is compressing. This bond is stretching, this bond is compressing. Then such kind of stretching called as anti-symmetric stretching. So one atom which is stretching, one particular bond is stretching, the other bond is compressing. And when this particular bond is stretching, the next one will be compressing. So it is called as anti-symmetric stretching. This one is called as symmetric stretching because both will be having same kind of mode. If this atom is going to, this particular bond is going to stretch that stretching mode, this one also will be in the stretching mode. If this is compressing mode, this one also will be compressing mode. So it is this, if this atom is coming close to this atom, central atom, which is in the black color, this atom also coming towards that central atom. Both are having same kind of mode of vibration. Then it is called as symmetric stretching. Stretching happens symmetrically. But in this case, it is anti-symmetric because one particular bond is stretching, the other one is compressing, and vice versa. Okay? So such kind of vibration is called as, or such kind of stretching is called as anti-symmetric stretching. And we have different other vibrations, which is one is rocking, and then wagging. This is, you can see this again. Okay. So these two are stretching, and this rocking, wagging, twisting, and scissoring. Okay, these are depending on their angle. Okay, this depends only your distance from the central atom, that is r. It depends only on that r. This one also depends on that angle of stretching. So that means I mean vibration. So that is these are bending modes. These are stretching modes. So that you can see in rocking, you can see these are having this kind of vibration. Okay? And in wagging, we have this kind of vibration. So in rocking case, you can see this vibration is in that plane itself. Whatever you are seeing on this screen, the vibration happens with the change of angle, where the bond length is fixed, r is fixed, the separation from the central atom to this atom, then this green color which is fixed, but the angle will be different. Okay, so here angle is going to change, and it is called as rocking, and rocking will happen in this plane, in this plane of the screen that you are seeing. But in the case of wagging, it is happening to the back and forth action. Back and forth action will come. Okay, you can see. That is wagging, and then we have twisting. Twisting means one go out of this plane, out of the screen. The second one go into the screen. Okay, such kind of action. This atom you can see in twisting. This atom will be coming out of the screen. The other one is going into the screen. Okay, so such kind of vibrations, that is called as twisting. These are having difference in angles. These four are having difference in their angles. Their distance from the central atom is fixed. R is fixed. Bond length is fixed, but their angle will be different. Okay. So with respect to that angle, it is going to change, or it is vibrating. Okay. So these are called as bending modes. Right? That's why it is called as bending modes. These first two are stretching modes because their R is going to change. The distance from the central atom, this bond length, that is going to change. But in this case, bond length is fixed, but the angle is going to change. So these are the bending modes. These four are the bending modes. So this is twisting. Then scissoring, you can see from here like a scissor, it will go. So central atom is fixed. So these two atoms come close to each other and then it will go away from each other. So such kind of vibrations are called as scissoring. So this is another kind of bending mode vibration. It is called as scissoring. So all these kind of vibrations which are possible for the different molecules according to their bonds, whether they are single bonded, triple bonded, or double bonded, or their atomic atoms which is in that molecules. All this will determine which kind of vibrations will happen in those molecules. Okay, so basically we have two vibrations which is in the stretching modes, which are symmetric stretching and anti-symmetric stretching, and four vibrations which are in bending mode, which are rocking, wagging, twisting, and scissoring. Okay, so basically vibration modes are two. One is stretching, another one is bending. And in stretching mode, we have symmetric stretching as well as anti-symmetric stretching. And in bending mode, we have rocking, wagging, twisting, and scissoring. Okay, I hope you understood these different modes of vibrations. So basically, we can say vibrations. You can say these vibrations as stretching modes vibration. And then we have bending mode. And in stretching mode, we have symmetric stretching as well as anti-symmetric stretching. And in bending mode, we have other four modes. These are fundamental, okay? These are the basic modes of vibration. So we have scissoring, modes. Scissoring. Then we have wagging, twisting. Then rocking. So these are the different bending modes which are possible to these molecules. Okay. So these are the basic modes of vibrations which we can observe in molecules. Now, what actually happens when this happens, when you are having that infrared radiation, that molecules absorb this infrared radiation if their uh, molecular that bonds or the atoms which are having that particular vibrational frequency in that particular molecule, then they absorb that IR radiation, start vibrating. Okay. For example, if you consider the formaldehyde molecule, is an example. So if you consider formaldehyde molecule, we have C double O, and we have hydrogen. This. Okay. So if you consider this carbonyl group, this C double bond O carbonyl group, this particular group. So this can go, and I'm talking about this CO group here. Okay. So this CO group, which is double bonded, I'm just showing it as a single one for some nodes of vibration. So this particular molecule, which can have a stretching mode of vibration, so they will go back and forth like this. So this can have stretching mode. Means that the oxygen which can go away from this carbon like this. So basically that is double bond. I will just show you here. It is as a single one. Or otherwise it can come very close to this carbon. So by means it can go, it can perform this stretching mode vibration. Okay. So each time this will, this bond length R will increase this time, and here it will decrease. So each time this kind of vibration will happen. Okay. So that is one possibility. Another possibility is that this C double bond O, that is a carbonyl group, which can wag, okay, which can go here and come back here. So this is also possible. So sometimes it will be in this oxygen can go here, and next time this oxygen will be over here. Okay. So basically it is wagging. It is wagging from this position. So this is also possible. For this case of this is the formaldehyde. Formaldehyde molecule. So in this case, these two are possible for this carbonyl group. Both these modes are possible. Let's, for example, as an example, let's say this is having a vibrational frequency. So this is vibrating. Okay, this is vibrating. So you are having something like a spring like this, and it can compress like this. So it will become like this when compression, or it can expand like this. It can expand like this. That is also possible. So both this will produce will produce vibration. So stretching and compression, that will produce vibration. Okay. So each time when you are having this stretching and compression, stretching, compression, stretching, compression, then that will produce this vibration, and that vibration will be having some frequency. Okay. So when that stretching and vibration happens like this every time, so this will be having some particular frequency of vibration, which means that with respect to that mean distance, your R is going to be varied. It will be increasing and decreasing. Again, it is increasing and decreasing like that, and it will produce some kind of vibration. And this vibration, let's say, for this particular case, formaldehyde case, if you are considering these particular vibrations having frequencies which are 2 hertz, for example, in this stretching mode, it is having some 2 hertz, and in the this bending mode, that is the wagging, so bending mode, it is having 4 hertz. This is not the actual values. I'm just giving you some example, okay, for easy understanding. Yes, so these are not the exact values. It will be having very high frequency, not 2 hertz or 4 hertz. They will be having very high frequencies. This is just as an example. I will take it as 2 hertz here. It is 4 hertz of vibrational frequencies. Now, suppose if you are putting this formaldehyde in a sample holder. So if you are having your sample here, what is your sample? Your sample is this formaldehyde. Okay, this is your sample. And if you are giving, if you are having some infrared radiation which is in that visible range, sorry, in that near IR range, and that is coming and interacting with this sample, which is nothing but your formaldehyde. Okay, so if the incoming radiation is, for example, 1 hertz, the incoming radiation or incoming IR radiation, which is 1 hertz, then this formaldehyde will not be having any problem with that 1 hertz, because it's carbonyl group. I'm not talking about CH bonds now. I'm only focused on this carbonyl group. So considering that carbonyl group only, so this frequency 1 hertz will not affect. because these vibrations are at 2 hertz and 4 hertz. Okay? So the incoming radiation which is having 1 hertz, so it will just pass through this sample. And if you are having any detector at this point, if you are having any detector, now if you plot that graph, is the transmittance. Let's say this side we have transmittance, so that is in percentage T. And for example, this is your maximum value, that is 100%, and this is your minimum value, that is 0%. So the 100 means all the radiation which are transmitted through. Okay, 0 means not a single radiation of that frequency which is transmitted. So in x-axis we have frequency. Let's say this is in hertz. Now, if you detect this particular case for this formaldehyde carbonyl group, remember that I am not considering this CH bonds, so they will be also having some kind of vibrations, and associated with that there will be absorption also. So I am not going to discuss about that. This is for just understanding. So if you are considering this in formaldehyde, we are considering this carbonyl group C double bond O. Then we have this incoming radiation which is 1 hertz. It will not interact with this molecule because its stretching or bending frequencies are not equal to the incoming radiation frequency, which is 1 hertz. Okay, so this 1 hertz will be detected by this detector, and we will get, for example, if this is your 1 hertz, then you will get the maximum transmittance, because all the radiation with 1 hertz will be transmitted through the sample. It will not be get absorbed. Now, if you are sending 2 hertz frequency, then what will happen? When you are having 2 hertz frequency, this carbonyl group is having stretching mode vibration at 2 hertz. You can see from here. So this carbonyl group is having stretching mode vibration at 2 hertz. So this carbonyl group absorb this incoming radiation because its frequency of this incoming radiation matches with the vibrational frequency of this carbonyl group. Then that absorbs this radiation. In that time, we will not get any output. We will not get any output at the detector. So that means your graph will be like, so this is your first case, then your second case will be, for example, no radiation is coming. In that case, you will be getting a 0 here. So if this is your 2 hertz frequency, then you'll be having 0 transmittance because all the radiations will be absorbed. Now let's consider the incoming radiation, which is, for example, 3 hertz. Let's consider the case for 3 hertz. Then in that case, this radiation is coming with 3 hertz frequency. And when it comes to the sample, it will not interact because there is no vibrations which is at its frequency, which is equal to 3 hertz. So it will just pass through this sample. And it can be detected at the detector, and you will get maximum transmission at frequency when it is frequency at 3 hertz. So it is at 100. And then if you consider another case, which is 4 hertz, if your frequency is 4 hertz, so your incoming radiation frequency, that is in the IR radiation range, and which is having 4 hertz frequency. The frequency start now coming and hitting with this sample. So now the frequency is 4 hertz. When it interact with the sample absorbs that frequency. Okay, because the sample is having a vibration at 4 hertz, which is the wagging, or which is the bending mode vibration. So because of that, the sample will absorb that particular frequency, which means that this carbonyl group, if it is getting some kind of frequency which is equal to 4 hertz, then it will start wagging. So it will absorb that radiation and it will start wagging. Okay, so when it is 4 hertz, The sample absorb that frequency and you will get no radiation at the detector end. But it will not absorb all the radiation. Normally, if you are considering the sample, it will not absorb all the radiation because it is not the only one photon which is coming, number of photons which will be coming. So we are just representing only one case here. So there will be different radiations like this. There will be number of photons which are coming like this. Okay. So all these photons will be having same frequency, that is 4 hertz. But the number of photons which are coming, different number of photons coming. So all those number of photons will not interact with this carbonyl group. Some of those photons will not interact with the carbonyl group, and those photons can come out and can be detected at the detector. Okay. So all the photons will not interact with the carbonyl group. Because of that, some of these radiations can be observed at the detector. But majority or many of these photons with 4 hertz can interact with this carbonyl group and which can be absorbed by that carbonyl group in order to have that wagging vibration or the bending mode vibration. So all the photons will not absorb, will not be getting absorbed by these molecules because some photons will not interact. For example, some photons which are coming through this bond, carbon hydrogen bond, they will not interact with. Only those photons which are coming to this C double bond O group, they only will get absorbed. Okay, so any photon which is coming in through some other bonds or some other spaces through the sample, they will not be interacting with this group. Okay, so they will not get absorbed. Majority maybe get absorbed, but some photons will not be interacting with this carbonyl group. So those groups, those photons which are not interacting will not get absorbed. If any of those photons which are interacting, they will get absorbed. So normally we will not be having intensity will not become zero, but it will be decreased. Okay, if you are sending 100 photons from here, so in that 100, some 80 photons may interact with this carbonyl group. 20 photons may not interact with this carbonyl group. So whatever this 80 photons which are interacted with this carbonyl group will get absorbed. Okay, and remaining 20 which are not interacted with carbonyl group, so they will not have any effect because of that sample. So they will come out from the sample and can be detected at the detector end. So in that case, 80 number of photons get absorbed, which means that 80% of the total photons get absorbed. So we will get at 4 hertz, we will get around 20, which is not transmitted in the transmission spectrum. So only this much of which is at 80. Sorry, this is the transmission spectrum. So 80 are absorbed, so only 20 will be 20 will be transmitted, right? So it will be in the 20 are transmitted, right? So 20, okay, that's so 20 which are transmitted. So 20% will be transmitted. So your point will be like this. And for all other radiation, for if you are considering only these two frequency, then for all other radiations will be having maxima. And if you plot this graph, then it will come like this. It is going to 0, and then come back to this, and again coming back, going like this. So analyzing these frequencies, one can say that by analyzing these frequencies where you are getting these peaks of absorption or peaks in the transmission spectra, which is corresponding to that absorption. Okay, and analyzing this frequency, we can predict which kind of molecule which is present, or which kind of bonding, okay, which is present in that particular group. Okay, so by analyzing this spectra, we can say what kind of molecule you are dealing with, or in that sample, which kind of molecule is present, or which kind of bonding is present, which items are present in that particular molecule and what kind of bonding it has in that particular molecule. That can be predicted by studying this infrared spectra of any sample. Okay. Now, this is not the reality. In reality, we'll be having some different scenario because in reality, we will not plot this graph in frequency. Instead of that, we will be plotting that uh, in wave number, and there is some specific reason for that. We just check that. But why we are plotting it in the wave number instead of frequency? That is the important thing. So if I am plotting in reality, how it will come? So in reality, for example, this is your transmission spectra, your percentage of transmittance. Okay. So this is, for example, this is your maximum value, and you are having centimeter inverse in this x-axis. That is nothing but your wave number. Okay, and normally we'll be having from 4000 to 0, almost to 0 wave number. We'll be having like this. We are, and then we'll consider. Let's consider some different spectra. So let's say the spectra is like this. So also denote this. So this is 4000. Then let's say somewhere here we have, let's say this is 500. 2000 of that. Then we have here some 3000, right? Then here we have some 1000. So this 500 will come. This will come somewhere here. So that is your 500. So all this in centimeter inverse. So this is in wave number. So we have to convert that frequency, this frequency into wave number. And then if you are considering frequency, it will be having very high value. But when you are considering in that in centimeter inverse, we have some low value. So that's why it normally represent in centimeter inverse. So you check that what is the advantage of representing this in centimeter inverse instead of this frequency. Okay, so now if you consider this particular case, and let's say this is your spectra from that infrared analysis, we'll be having some spectra like these, for example. This is what your spectra look like. As an example, for some particular sample, you are getting like this. So this is the actual spectra. In experiments, you will be plotting this transmittance against this this wave number. This is wave number, which is in the centimeter inverse. This is your transmittance. Y-axis is in transmittance. And in this particular case, up to some 1800 range, around this range. Okay, so up to this value, we call this as the functional group region. This is your functional group region. And the remaining thing, that is from 1800, around 1800 to this 0. This is the fingerprint region. Fingerprint region. So this fingerprint region means those molecules will be having some molecules will be having some fingerprints, so which means that some particular kind of vibrational sequence, vibrational peaks, which are associated with some particular molecules. Okay, they will not change. Okay. Such kind of absorption, that spectra, the IR spectra, which is called as fingerprint spectra or fingerprints of that particular molecule. And this region from 1000 around 1800, that is 1800 centimeter inverse to 0, we have this fingerprint region where it will give you the whole molecule. And if you consider, for example, some molecule, let's say this, for example, formaldehyde itself, if that molecule is having some particular kind of infrared spectra from 1800 to this 0, then they will be having some peak in this range, which is associated with that particular molecule only. Okay? So that will give you that kind of molecule, which kind of molecule it is, and which is called as the fingerprint region. And the second region, which is the functional group region, which will give you the different functional groups which present in that molecule. For example, OH group, in some particular case, OH group, or CO group, CH3 group, CH2 group, such kind of functional group, different functional groups. Presence of those functional group will be given by 4000 to some 1800 centimeter inverse of it. Okay. So, for example, if you consider this particular peak, and this is associated with this particular wave number, and that will be associated with one particular functional group. For example, CO. Okay, that is the carbonyl group. If carbonyl group is present, this particular peak will be there for sure. Okay. Similarly, if this peak which is associated with some other kind of bonds, other kind of group, which we are looking, for example, OH group, if it is, okay, this wave number is correspond to that OH group which is present in your molecule, and then this particular peak will be there. Okay, so this side of the spectra, which will give you different functional group which is in your molecule, and this side of spectra, which will give you the fingerprint region, which is the fingerprint of certain molecules. Okay, that molecule structure it will give. Okay, so that is the different region that is in the IR spectra, and this is the normally this is the practical IR spectra, how it look like. I'm just plotting it as a roughly. You can search for some realistic samples how the IR spectra will look like. And also we have different frequencies of wave number which are associated with different groups which may be present in your sample. Okay, in the present case, we are having this carbonyl group in that formaldehyde. So that carbonyl group will be having some particular wave number. When you are taking that this example, we are considering it as 2 hertz and 4 hertz, but it is not the right values. But they will be having some values for that stretching and wagging vibrations. They will be having some particular value, and that is associated with that CO bond only, C double bond O bonds only. And if you consider any other kind of groups which may also present in different molecules, for example, you can consider the group OH group. As I said, OH group, if it is present in your molecule, then you will get a peak in the range of 3650 to some 3590 wave number centimeter inverse. And if you are having, for example, another group which is CH3, let's say CH3 group, which is also present in your sample. So in that case, for example, like double bond CH3. So in this case, we will be having 208 2880 to some 2860 centimeter inverse. Similarly, if you are having some CH bond, which is at there are different kinds of that. So let's say 200, 2900 to some 2700. And if you're having a double bond CH kind of a functional group which is present, then we will be having a different frequency which is at 3700, sorry, 3100 to some 3000 centimeter inverse. Okay, so these are some examples. You can look for the IR spectroscopic table, then you can get for all the groups what is the corresponding wave number which you can get. Okay, so if you are not knowing what kind of functional group which are present in your sample, then by studying this IR spectra of that particular sample, then you can say which kind of functional group which are present in that particular sample. Okay. Okay, then now we will discuss about. Okay, we can we will discuss something about the different. Um, you can also assume with the bonding. Otherwise, you can just check that table. Then you can understand which kind of. For example, if you are having that C double bond C kind of bonding, then it is at 1680 to 1600. So all this you can find out from that particular table of IR spectroscopy. And if you are having these different groups, alkaline group or such kind of groups, these functional groups, you can get those kind of information from your IR study. Okay, now we will discuss some of the theoretical part of this IR spectroscopy. So how this is happening in theoretical? I mean, what is the theoretical basis of this particular IR spectroscopy? Now, as I mentioned, when the radiation comes and hit these bonds, when they absorb that particular frequency, or if their frequency is matching with their vibrational frequency, they absorb that particular frequency. Okay, so we have to assume these molecules as an oscillator. Okay, so now we will consider these molecules as an harmonic oscillator. Molecule as an harmonic. This is harmonic oscillator. Okay. Molecule as harmonic oscillator. What that means? That means the frequency of vibration which is same. Okay, the frequency, that is the displacement on both sides which is same. Okay, there is no anharmonicity in that particular vibration. So the vibration is symmetric, we can say. So the harmonic oscillator case, what will happen? For example, if you consider, and in that in symmetric and anti-symmetric, I will give you another example. If you are considering the example x, y like this, x, y. Let's say we have some one molecule which is like this, x and y. Okay. So symmetric stretching case, what will happen? Both will come close to this X at the same time. Both will go away from X at the same time. So this is symmetric stretching. So that's symmetric stretching. So both will be coming towards that central atom at the same time. Both will be going away from the central atom at the same time. So both will be having same kind of vibration, or with the same kind of mode, which is changing. The bond length will be in the same direction. So if this atom which is going away from the central atom, this one also going away from the central. But in the case of asymmetric stretching, what will happen in this particular example, if you are having this XY like this, and for asymmetric stretching, let's say this atom comes close to the X, at that time, the second atom will go away from the central atom. And also, when this comes close, this will go away from the central atom. So this is the asymmetric stretch. Okay, this I'm just giving you another example for that, for understanding. Okay, so coming back to this harmonic oscillator, considering the molecule as an harmonic oscillator, which is an harmonic oscillator, then E equal to, let's say, this energy associated with the harmonic oscillator. Consider the molecule as an harmonic oscillator, that is HO. So it has allowed energies or energy associated with those harmonic oscillator or vibrations, which will be given by E equal to H nu, oscillation frequency, that is nu oscillation, times V plus R. This you might have studied. Instead of V, we'll use N. In quantum mechanics, if you are saying En for harmonic oscillator, it will be having H nu times N plus R. Okay. So instead of that, instead of this N, we are using V, and this V here is the vibrational quantum number. Vibrational number. And what is J? J is the rotational quantum number. When we discuss about the rotational spectroscopy, in there we discussed the quantum number J, which is the rotational quantum number. In here we have V, which is the vibrational quantum number. And this we can take values from 0, 1, 2, 3, etc. Now, what is this new oscillation? New oscillation is the oscillation frequency or oscillating frequency of that particular harmonic oscillator. That will be given by 1 by 2 pi root K by M, if you are considering that K as your force constant. So if you are considering, again, if you are considering that case of the spring, your spring which is attached to some mass or something. So this is like this is attached to some mass M. Then if it is vibrating, then you can get that frequency of vibration, which is nothing but 1 by 2 pi root K by M. And this K is associated with the force constant of that particular spring. Same scenario we have taken from that expression and applied in this vibration of molecule, and we will get the oscillation frequency, mu oscillation equal to 1 by 2 pi root K by M. So this is your energy. In terms of wave number, how we can write it is, so energy in terms of wave number, that is denoted as G of nu, and this G nu So I will write here. This will be E by hc. So energy in terms of wave number, that is E by hc. That is denoted as G nu, and that will be given by nu oscillation divided by C. One h, this h will get cancelled, and this nu oscillation by C into V plus half. So this is in wave number. Or you can write G of nu, which is equal to omega C times V plus half. And where omega C is nothing but nu oscillation divided by C. So now, if you are considering this case, let's say, if you calculate G nu corresponding to different V value, so G nu will be equal to, in first case, what will happen when V equal to 0, this will become 1 by 2 omega C. This is 1 by 2 omega C. Then V equal to 1, what will happen? This will become 3 by 2. So 3 by 2 omega C. The next is 5 by 2 omega C, 7 by 2 omega C, and so on. So this is at V equal to 0. Similarly, this is at V equal to 1, V equal to 2, etc. So in that case, the energy in terms of wave number will be coming as 1 by 2 omega C, 3 by 2 omega C, 5 by 2 omega C, 7 by 2 omega C, like that. Okay. Now, if you are plotting that, if you are plotting those energies, then, for example, the lowest one is this, when V equal to 0. Then we have second one, which is your V equal to 1 case. Then next one is V equal to 2 case. Then we have V equal to 3. Same. Separation should be same, because why separation should be same? Because when you are taking that nu bar, if you take nu bar, that is the difference between those energy levels, okay, in terms of wave number. So this will give, if you consider these two adjacent energy levels, then it is 3 by 2 minus 1 by 2 omega C, right? Or you can say this is omega C into V dash plus half minus omega C into V double dash plus half, where V double dash is the highest energy level. Sorry, this V dash is the highest energy level. You have to subtract from the highest to lowest. Okay, so this V dash here, it is the highest energy level, and V double dash is the lowest energy level. Or we can say that it is the higher energy level and lower energy level. Okay, not the highest, but I can write it as higher and lower. Highest is something different. So this is higher energy level. This is the lower energy level. So I'm just considering the two adjacent energy level. Okay. So V dash and V double dash. V dash is the highest, higher one. V double dash is lower one. And in that case, if you take this these two, then if you substitute this V dash, for example, in the first transition, for first transition, that is from the highest of these two, that is V equal to 1 to V equal to 0. In that transition, what will happen to this mu bar when V equal to 1? So when V equal to 1, that is the highest one, V dash, which is equal to 1. So that will give you 3 by 2 omega C minus V double dash is 0. That is the lowest one. Sorry, lower one. So this one is 0. So it will be 1 by 2 omega C. And this will become omega C. And if you take any adjacent energy levels and subtract that two energy levels in wave number, then you will get omega C as the difference. So the separation between these energy levels will be omega C always. Okay. Then next we have the next energy level like this, same way. So the separation between each of these energy levels should be same. So now you can connect all these lines. You can have a structure. You'll be having like this. Okay. So these are the vibrational energy levels of by using this particular equation. So this is your V equal to 0. This V equal to 0. V equal to 1, 2, 3, 4, etc. Correspondingly, you will be having energy of omega C here, 3 by 2 omega C, then 5 by 2 omega C, and so on. And what is this? This is nothing but your that interatomic distance, R0, mean distance of that. If you are considering that distance between those atoms, so each time those distance will increases, so this will increase. Each time this will increase. Okay. So that's how your energy levels look like. And the transition, I have told this transition from V1 to V2, and the transition rule, selection rule for this transition is delta V should be equal to plus or minus 1, similar to that of rotational transitions. So from one energy level to next vibrational energy level, the transition happens. For example, what we are told, we have discussed here is the transition from V equal to 1 state to V equal to 0 state. So this transition we are talking about in this case. And another transition which is possible, which is from this 2 to 1 or 3 to 2, and in the reverse also. So like 2 to 3, 1 to 2, 0 to 1 also possible. In that case, it will come as minus 1. So the transition is possible only between this adjacent energy level. From 2 to 1, this transition, sorry, 2 to 0, this is not possible because it is against this selection rule. Delta V should be equal to plus or minus 1. It can go up, it can go down. When it is plus 1, it is going down from higher state to lower state. So that delta V will become 1 minus 0 equal to positive. And in the other case, it can go from 0 to 1. In that case, delta V will become 0 minus 1, and that will become minus 1. That is also possible. But from 2 to 0, it is not possible, or 0 to 2, it is also not possible because the delta V value will become plus or minus 2. That is not allowed. It is forbidden. So only this delta V equal to plus or minus 1 is allowed. So this is the selection rule for the vibrational transitions. Now, in normal case, okay, if you are considering the vibrations, where we have considered it as a harmonic oscillation, but in normal case, it will not be an harmonic oscillation. Okay, in that case, we have to consider the anharmonic oscillator. Okay, so then we have to treat for example, analyzing those molecule as a perfect harmonic oscillator. Then we have only this fundamental band of frequencies. But in experiment, we have also these overtones, as I discussed earlier. We have fundamental band as well as some faint or some low intensity spectral lines also coming along with that fundamental bands. So then that means we cannot treat these molecules as a harmonic oscillator. Instead of that, we have, in reality, it will be anharmonic oscillator. So considering this or assuming these vibrations as of an anharmonic oscillator. So in that case, what will happen? The energy E nu will become. So these are coming from this quantum mechanics, the energy calculations. We have to consider Schrodinger equation, apply potential and other parameters into that Schrodinger equation, solve for the energy. Okay. Similarly, what we are doing for this particle in a box or harmonic oscillator problem, we are having that potential, apply that potential, wave function, all those things, then we will get what is the energy corresponding to that particular case. Similarly, we have to apply same concept here. We have to give all those parameters, potential, then we will get what is the energy associated with this kind of vibrational motion. In case of harmonic oscillator, same as that of in the case of quantum mechanics. Similarly, we can calculate what is the energy associated with anharmonic oscillator. So that is coming from quantum mechanics, and that is given by E nu, that is equal to hc omega E V plus half, sorry, this is omega C, omega C V plus half. Then we have minus hc omega 0 E into V plus half. You can denote this letters with some other possible letters, because in some books it will be written. So similarly, wave number, in terms of wave number, this will be equal to omega C into V plus half minus omega 0. This is omega E. So I think this also we can replace with omega E, or you can use omega C in all those, for all those values. This is also omega E, or you can consider it as omega C also. So if you are using omega E, then you have to replace these things also omega E, or you can put this as omega C in everything. I'll just put it as omega C right now. Let us put it as omega C times V plus half Here also omega c. So this is omega c times xc and then v plus r. Only this term is additional here. Okay, this hc is nothing but multiplying this whatever we are having that in wave number, multiply that with hc, you'll get energy. That is as simple as that. So this is the energy in terms of wave number with this considering that molecule as an anharmonic oscillator. So this term is additional in case of anharmonic vibrations. Okay, so in this case, what will happen to this nu? Or if you calculate that nu bar, okay, this nu bar, what will happen in this particular case? Okay, before that I will say this xc. This xc is the anharmonicity constant. Anharmonicity constant. And that xc is very small than this this here xc is much smaller than omega c, and hence there will be a very small decrement while going to the higher energy levels because of this term. Okay, and if you calculate this nu bar, you will get omega c into v minus omega c into xc v square minus omega c into xc v cube minus etc. So these are the higher order terms. Okay, these are higher order terms because of that anharmonic vibrations. This is for your first case. This one. Here we have the higher value of v equal to 1. That's why it is coming as omega c only. So this is this nu bar is omega c. That v value, which is differ from the difference between these two, which is equal to 1. So we'll get omega c. So omega c into v. That will become here it is omega c. And here we have omega c v minus omega c x c v square minus omega c x c, etc. And the selection rule for this case, when you are having this anharmonic kind of vibration, so delta V will become plus or minus 1. That is for fundamental case. Then we have plus or minus 2, plus or minus 3, and so on. And this plus or minus 1, which is the selection rule for fundamental mode, okay, or fundamental frequency. So this one is for fundamental frequency, and this modes plus or minus 2, plus or minus 3. These are for overtones. I will explain those things in the next section. So these are the overtones. Okay. So because of these additional terms, this anharmonic oscillator, we have this additional term which is minus omega e xc times v plus half. So your energy levels now what will happen? So while you are going from this lower state to the upper state or higher energy levels, so here you are having that v equal to 0 state, then you are having your v equal to 1 state, then your v equal to 2 state, okay? Then your v equal to 3 state, and when you go above, your energy level difference, that is going to get reduced. That will be like this. Why? Because of your, so this is your potential curve. So I will explain how this is coming in this form. This actually this will come like the exact fashion. If you are looking at that potential, you will be going like this. Okay. I will explain how this curve is coming in the next class. So this is coming in like this step. Actually, that is coming from your R. You have to consider that R in this axis. And this is your energy, potential energy, which will come here. So like this, you have to put. I will explain those in next class. Anyway, that because of this energy, additional term in your energy, in this is in wave number. So that will come, that because of that, when each time when your V is larger, V becomes higher. So when your V is going to become higher, in each time, I think I have made one mistake here. This should be square here. There should be one square here. V plus half square plus etc. Here also I am having that square term. This will be plus etc. Higher terms. This is also square. V plus half square will. That's why it's coming as V square, V cube, etc. So additional terms also will come. So remember minus HC omega C XC V plus half square. Similarly here we have omega C XC. This is XE and V plus half square. This V plus half square. So when your V is larger here, when your V gets larger, square of that you have to consider, and you have to subtract that from this term with when you are not monicity. When you are considering harmonic oscillator, molecule as harmonic oscillator, you have only this term. With that term, you have to subtract this additional terms. Okay, so when your V is larger, you will get higher value in this portion, this term. Your value will be larger, and you have to subtract that from your the energy levels which is present corresponding to that harmonic oscillation. So in that case, it will be coming when you move away, when you are going up, V equal to 0, V equal to 1, V equal to 2, etc. When you go up, your energy gap, this energy gap will get reduced. You can see from here. So the energy gap is getting reduced when you go higher for a higher V value. Okay. Similarly, if you are considering this nu bar, what is this nu bar? This nu bar is the wave number corresponding to different transition, which means that if it is coming from 1 to 0, which will give you first nu bar, that is mu1, for example, fundamental one. And then if it is coming from 2 to 1, it will give another radiation, another frequency. Okay, each of these transition, you will get a different frequency radiation which is coming out. Okay, so this is, let's say this is mu2 bar. We are putting it bar because this is in wave number, not in frequency. So in fundamental one, we'll be having very high intense. Okay, so this transition will be, for example, if you consider these, in this case, if you are considering V equal to 0, V equal to 1, V equal to 2, V equal to 3, V equal to 4. So that variation should be there. First, I will consider some higher value. Then we have reduced. Something like this. So if you are considering these are your V is equal to 0, V equal to 1, V equal to 2, V equal to 3, and so on. Now, if you consider this transition from 1 to 0, that is corresponding to that fundamental line, okay, or you can also take from 0 to 1 also. I will take that one. So if you consider 0 to 1 transition, that is also possible. Then your delta V in this case is -1. So you will get one spectra corresponding to this case. Okay, what will be that spectra? And that spectra will be very high intense. This spectra will be high intense because it's going from 0 to 1. The energy level difference in this case is larger. Okay. In the next case, you will be having the transition from V equal to 1 to 2. Okay, and V equal to 2 to 3, all those possible. Another possibility is that you can go from V equal to 0 to 2. This is also possible in this case, because when you are considering that anharmonic case, we have selection rule delta V equal to plus or minus 2, plus or minus 3, all those things. Okay, these things are also there. So because of that, you will get these transitions from 0 to 2. Then we have 0 to 3. Transition is also there. Okay. And we have 0 to 4, all those transitions. And in those cases, we'll be having faint lines. The first one will be very intense, and the other transition will be having low intense spectra. The intensity of this will be getting reduced this time. And these are the overtones which are coming from selection rule plus or minus 2, plus or minus 3, plus or minus 4. Like that. This is your fundamental frequency. So this is your fundamental line, and these are the overtones, which are less intense as compared to fundamental line. And if you plot that in intensity, then we can plot that. So similarly, you can have this side also. Okay. When you are having delta V equal to plus 1, okay, then it will be coming in this side. Okay, so that you will get something like this first line, then you have second line. So the suppression will be same, almost like this. Then third one will be have faint line. Again, faint line. When it go away from this fundamental line, its intensity going to be reduced. And if you plot that in intensity spectra with that height expression, so fundamental line will be having this high intensity. Then when it comes to the next, we'll be having low intensity. Again, the intensity get reduced each time. So it will be something like this. Each time intensity will get reduced. So you just check that what is the, I think that should be closer when you go into that deeper level. It should come close to each other, because when you go from here to that, suppression should get reduced, right? So the spectra, you're drawing the exact way. So the first fundamental line will be like this, very high intense, and second one will be having like this, and third one will be having less intense, and fourth one we have, we should draw this somewhere here if you want to get it in a clear way. So that is corresponding to this line. So that is not that much intense. The next one will come close to that, because when you go up, this energy level get reduced, and the separation between each energy level will be small. And similar to this side also, we have one, first overtone, and then you have second overtone, then third overtone, which is less intense, and fourth overtone. So it will be coming close to each other. And when you consider this intensity spectra, then we have to consider that this is your fundamental line, and this is your first overtone, and second overtone, third overtone, fourth overtone, like this. This is your first one, second overtone, third, fourth, fifth. They will be very close. So this will be your spectra, how it look like when you are plotting that in terms of intensity. So this is your intensity versus wave number. So it will be like this. So these values are correspond to delta V, which is equal to -1. This is correspond to +1. This is correspond to delta V, which is equal to -1. Okay. So I think we can stop here, and we will discuss more about this vibrational spectroscopy in the next class.